In this lesson, we're going to be looking at some graphs of polar equations. A polar equation is an equation expressed in terms of r's and thetas. So we've graphed linear equations like y equals mx plus b. We've graphed quadratic equations that were parabolas. We've graphed all sorts of equations up to this point. However, now we're going to start graphing them in a coordinate plane. And each of these graphs actually have kind of, I guess you could say, a distant cousin that looks identical to it, that's going to be in this polar coordinate plane that contains r's and thetas instead of x's and y's. Here's some examples of some polar equations. Maybe you have just like r equals 3. You might could have r equals 5 sine theta. You could have r equals -3 over the cosecant of theta. So we're going to be involving sines, cosines, all those trigonometric values, along with some coefficients, some radii. You have transformations. All those things still apply when you're graphing in polar. So let's start with number 2 here. Let's graph r equals 2. Very simple. Now what this means is no matter what no matter what angle that you're dealing with, your r value is always 2. So what if your angle is 0, then r is 2. What if your angle is pi over 6, then your r is 2. What if your angle is 90 or 5 pi over 6? No matter what angle you have, your r value is 2. So we're going to go around in all these places. We're going to put an r value of 2. And what you have is a resulting circle. And I'm going to go ahead and connect my dots, and here's your circle. And there you see your graph. So what if radius equals -4.5? Well, again, that's saying no matter what your angle is, that means that your radius is -4.5. So what if your angle is 0? Then your radius is a -4.5. And we're going to assume that each line counts for 1, and it does. So there's 2 and 4. So if my angle is 0, then my radius is -4.5. 1, 2, 3, 4.5. If my angle is 90, which would be up here, then my radius is -4.5. Remember just to go in the opposite direction. 1, 2, 3, 4.5. Since you're talking about a negative radius. What if my angle is pi? Then my radius is -4.5, which would carry me over here. What if my angle is 270? Then again, my radius is 4.5. So again, you're going to get a circle. No matter what your angle is, you have a certain radius, and that radius can be negative, and here's the resulting circle. Okay, now the next one's a little bit different. They're saying that your angle is always 60. No matter what your radius is, your angle must be 60. So what if you have a radius of 1? Come out here to 1, your angle would be 60. What if your radius is 2? Your angle is 60. What if your radius is 3? Your angle is 60. What if your radius is a 0? Then your angle is 60. It's still in the same place. What if your radius is -1? Then your angle, now to go 60, we're going to have to go in this direction. Your angle is still 60, which would actually fall there. What you're going to end up with in this case is going to be a slanted line. Now, what's cool about this is the angle that this line is slanted, I guess you could call it the slope, would be a 60-degree slope. So you're actually able to define the slope in terms of an angle instead of a rise and run. So what if your angle is -7 pi over 6? So if you have a radius of 1, now -7 pi over 6, that'd be -210. So if your radius is 1, to go in a negative direction, we have to go this way. So we're going to go 180 plus an additional 30, and you end up here. What if your radius is 2? Then you're going to go to the exact same angle. Your radius is 3. You're going to go to the exact same angle in this direction, and you're going to continue doing that. What if you have negative angles? Negative radii. What if your radius is a -1? You're going to go in this direction now. Since it's a negative, you're going to go in this direction still since it's a negative angle, but if your radius is like a -1, which would bring you to here, and then when you spin it, you're going to end up over here. So no matter how you choose your radius, your angle is -7 pi over 6, which ends up giving you this line right here. So you can kind of already see that, again, different equations would end up with the exact same graph. I could have graphed theta equals 5 pi over 6. And got the exact same graph because 5 pi over 6 and negative 7 pi over 6, again, remember the phrase, they're coterminal angles. Okay, starting with number 5, we're now graphing a little bit more complex equations. It's not just r equals or theta equals, which were circles and lines. Now we're graphing r equals 2 sine theta. And it says to graph the equation below, we're going to plot points using the table. So we've got some t-tables here. Then we're going to connect into a smooth curve. So let's zoom in. And here we're plugging into r equals 2 sine theta. Now we're plugging in our angles. You can see in our t-table, we're given the angles. And they have given, they've used the angles in the t-table that correspond with our angles, our exact angles here. And it also corresponds with 30, 60, 90, all those angles that we know the sine, cosine, and tangent of. So what we're going to do, we're going to plug these angles in. Let's start with 0. We have 2 times sine of 0. The sine of 0 is 0. 2 times 0 is 0. Pi over 6 here is 30 degrees. Sine of 30 is a half. 2 times a half is 1. Pi over 3 is 60 degrees. Sine of 60 is root 3 over 2. When you multiply that by 2, it gives you root 3, which when you start graphing, the square root of 3 is right at 1.7. Keep that in mind as you graph. Pi over 2, that's 90. The sine of 90 is 1. 2 times 1 is 2. And go ahead and finish it out. Just keep in mind when you're doing these like 2 pi over 3 and all these others, all students take calculus. Keep that in mind. Use your reference angle. So when we're doing 2 pi over 3, which is actually 120, you're going to use your reference angle of 60, which is right here, and you're actually going to end up with the exact same root 3, which is 1.7. So let's go ahead and plug the rest of these in, and here's what you're going to get. And now let's plot these values on our circle over here. So your first one is located at 0, 0, which is the origin. When you plugged in pi over 6, and here's pi over 6, you get a radius of 1. So at pi over 6, go out a radius of 1. And I want to notice or point out that here's 1, 2, and 3. So each tick mark counts a half unit. So that's a radius of 1 at pi over 6. At pi over 3, we have a radius of about 1.7. So here's 1.5. So 1.7 would be somewhere right. Let's see. Yeah, I believe that'd be right about maybe a little bit short of that. Let's see, did I mess up? No, we're good. At pi over 2, I believe is where we got to. We have a radius of 2. At 2 pi over 3, we have a radius of 1.7. So let's go to 2 pi over 3 and go out about 1.7 again, which was located about right in there. At 5 pi over 6, we have a radius of 1. So that falls back there. And then at pi, we have a radius of 0. So go to pi, and we're actually back to here. If you do these other ones, 7 pi over 6, which is located here, you have a radius of -1. So we'd go in the negative direction, which ends up back up here. And these points over here actually mirror image these over here. They'll lie in the exact same place. So let's go ahead and connect our dots and see what we have. And it actually looks to be another circle. Now this circle has been translated, doesn't look identical to the first one that we worked. Okay, let's do some more. Let's try to graph r equals cosine theta. And again, we're going to do some t-tables here. So I'm going to come over here to the side, and I'm going to plug in the exact same. We're going to plug in some thetas and give us some r's. So let's go ahead and plug in the exact same angles we did before. And there they are. So when we do the cosine of theta, the cosine of 0 is 1. Cosine of 30 is root 3 over 2. Cosine of 60 is going to be 1/2. Cosine of 90 is 0. And then it actually goes in the negative direction. Cosine of, let's see, that would be 120 would be -1/2. Cosine of 150 would be negative root 3 over 2. Let's go ahead and plot those points and see what we have so far. And there are those points. Now, if you were to continue this, you actually end up getting these same points over and over, and it looks to be another circle. Let's go ahead and connect the dots, and here's what you have. It would look something like this. The next one, we're graphing r equals -3 sine theta. And I'm just going to use this exact same t-table over here and just erase my values. Let's plug in, find the sine of these angles, and then multiply by -3. Here's the values you're going to get. And again, we're going to plot these in the exact same way. And as we graph these points, here's what my graph's going to look like. And it just so happens if you were to, again, because we will have to, if you were to plug in extra points, you do end up with the exact same repeating values. So let's go ahead and connect our dots, and here's your graph. And again, it looks like we have another circle. Okay, the next one, number 8, let me take my t-table and move it down so we can just use this exact same one. Now, I do want to reiterate the fact that these are the values that I'm using. You can use any values you want to for your angles the same way as X and Y's, and sometimes we might have to use extra values to get the full picture. So here's our graph. We're going to plug in all of our angles, take the cosine of it and multiply by 4. Here's what you'll get. And then as we graph these angles along with our radii, here's a look at our graph. And once again, you see a very similar circle. Now, I do want to remind you that when we have a negative radius, from what we said earlier, if you have a negative radius, you could actually graph a positive radius and take away a half rotation or 180 degrees, or take pi away. So if you wanted to graph this value that, or this point that I've got boxed here, if you want to do a positive 2 for your radius, then your angle, you could take away or add to a pi to that, or 180 degrees, and that's going to give you 5 pi over 3. And that's the reason we ended up at 5 pi over 3 comma 2 right there. Something else I do want to point out is they keep jumping back and forth on the scale, so be super careful, because here each box counted 1, 1, 2, 3, 4, and so on. But the next one is completely different. They let each box count a half, so be careful on your scale here. Connect the dots, and here's your circle. Okay, number 9. Now we're dealing with cosecants. We're graphing some cosecants. So the way I'd graph that, again, let me change markers. I do r equals 1 over the sine of theta, or the reciprocal of sine. To do cosecant, let's go ahead and clean our t-table up over here and start plugging in some points. So let's start with 0. We have 1 over the sine of 0. Now we got a problem here. 1 over the sine of 0. The sine of 0 is 0. 1 over 0 is undefined. So we will not have a value at the radius, or excuse me, at the angle of 0. The sine of 30, let's do that next. That'll be 1 over a half. Don't forget to flip it. 1 divided by 1/2 is 2. Pi over 3. 1 over the sine of 60 will be root 3 over 2. When you flip that, that'll be 2 over root 3. And since I'm going to type that into my calculator anyway, I'm just going to leave that as 2 over root 3. You don't have to worry about rationalize it. The sine of 90 is 1. 1 over 1 is 1. The sine of 2 pi over 3 is going to be the exact same thing as the sine of pi over 3. So we're going to have 2 over root 3. Then the sine of 5 pi over 6 will also be 1 over a half, which is 2. And then once you get around to pi, you're going to get the exact same values there. So let's go ahead and plot what we have and see what our graph looks like so far. And here are those points. And oddly enough, it looks like we might have a horizontal line by the looks of the graph. So very different from probably what you expected this to look like. Let's try another one. Let's do 1/2 secant of theta. And again, I'm just going to graph it right here on this same set of points there. So 1/2 secant of theta. Again, the way I'm going to graph this, that secant's also on top. When you bring it to the bottom, the inverse of secant is cosine. So I'm actually graphing 1 over 2 cosine theta. So let's plug these angle values in. Here's what you're going to get. And if the cosecant, when we graph, gave us a horizontal line, I've kind of got an idea what I expect to happen here. But let's go ahead and take these values that I just found for thetas and r's. Let's plot them, and let's see what this is going to look like. And here is our points, and my thought was correct. We actually have, it's hard to draw one, but we actually have a vertical line in this case. And you could continue on graphing more points. However, it says here using technology. You can check polar graphs by graphing device by changing the graphing mode to polar. Let me show you how to do this on Desmos, because Desmos actually will graph in polar coordinates. So here's Desmos. And there's a couple of things you actually have to do. First thing you got to do is go up here and let's change our setting. Click here and let's go down to, you see our two different grids. Let's click on our polar grid and click off of it. Now when you put in equations, you got to be careful not to put it in as x's and y's. You have to put it in as r's and thetas. So let's look at how we can do that. Okay, down here in the bottom, let me close this. Down here in the bottom left-hand corner, you also have this show keypad. We're going to have to click here, and you've got to be careful. We can't type in X's and Y's here. You're going to have to click on ABC. You're going to have to type your equation in with R's and thetas. So we're going to do R equals, let me find my equal sign here. That's a Z. Now we're going to have to go back here for equals, I believe. R equals, and I believe this was the secant of theta. Is that what we were graphing? 1/2 secant of theta. So let's do 1/2. Push the right key. And let's do the secant of theta. You can find under functions, trig, you can find all these different functions, or you can just type in SEC. And then your theta is found also under that ABC. It is located right here. So look what you have for R equals secant of theta, and yes, it is a vertical line, and you can see it there. That actually crosses at 1/2. You can see that right there. So now we'll start checking some of our other ones with technology. Let's look at the next one. R equals -2 cosecant of theta. So we're going to have to bring that to the bottom and actually graph it as -2 over the sine of theta. Do the exact same thing. Use your table of values, and I'm going to come over here once again and do it. So we're graphing R equals -2 over the sine of theta. I clean my t-table up there, and as I plug these in, here's what, once again, you're going to get. And then as we plot those points, let's scroll back down to our graph, plot those exact same points. Here is what your graph is going to look like. So there's my dots. I connect it with my line, and then once again, I do get that horizontal line. We can go back and let's try Desmos again. So we're graphing. Let me erase what I have here. We're graphing -2. Let me go back to my other keyboard here. We're graphing -2 times the cosecant of theta. Once again, you can find cosecant under functions if you would like to use it. The cosecant and then ABC is where you find your theta. So here's -2 cosecant of theta. Let me zoom out, and it is once again a horizontal line.